All right, let's jump right in. We're going to talk about this kind of brilliant trick. It's super simple, but crazy powerful for finding the fastest way through these giant networks. It's called bidirectional search.
I mean, just think about it for a second. Our whole world is basically one giant web of connections, right? You've got your friends on social media, flights zipping across the planet. It's all just one massive network. So the real question is, when you have a network with billions of points, how in the world do you find the shortest path from A to B without, getting totally lost in the process?
So, to even start tackling this, we've got to put on our computer scientist hat for a minute. And here's the wild part: once you start looking for it, you see that everything is a graph. And that is the absolute key to unlocking this whole problem of the path.
And these images just make it so obvious. Look at this. On one side, you've got airline flight paths. The airports are the dots, the nodes, and the flights are the lines connecting them. And on the other side, a social network. People are the dots, friendships are the lines. It's the exact same basic idea, the same structure.
And it goes way beyond that. The same structure can describe how biological cells move around, or even how web pages link together to create the internet. You have these systems that seem totally different, but underneath it all, they're running on the exact same playbook.
Okay, so let's just nail down a quick definition so we're all on the same page. A graph is just a fancy way of saying you have a bunch of dots, which we call vertices or nodes, and they're connected by lines, which we call edges. That's it. It's how we model relationships, and it's totally central to what we're digging into today. And that brings us right back to the big, hairy problem. When you're looking at a graph with billions of nodes, I mean, think about the entire internet, or every single person on Facebook. How on earth do you find the quickest route from one tiny point to another? Well, the first thing you'd probably think of is what we might call the brute force way, right? You just start where you are, and you start looking around one step at a time. This has a name. It's a classic algorithm called breadth first search, or BFS for short. It's super simple. You start at point A, then you check all of its direct neighbors, then you check all of their neighbors. You just keep going out layer by layer.
And this is where you see the problem, right? The search expands just like a sound wave. It just gets bigger and bigger and bigger. And the area you have to cover grows exponentially. It gets out of control so fast. You end up searching this huge part of the graph that's completely useless for finding your path.
But what if there's a better way? This is that aha moment. The one little idea that just changes the entire game. What if you don't have to search that whole massive area at all? The folks over at Geeks for Geeks put it so simply. But what if we start search from both directions simultaneously? That's it. That's the question. Instead of just starting at the beginning, what if you also start searching from the end at the same time? Here's the perfect analogy. Imagine you're lost in a gigantic maze. If we send one person in from the entrance to find you, man, that could take forever. But what if we send someone in from the entrance and you start working your way back towards the entrance at the same time? You're not looking for the exit anymore. You're just looking for each other. You're going to meet in the middle way, way faster. And that right there, that's the whole idea behind bidirectional search. It's not one giant slow search. It's two small, fast searches that are basically in a race to see who can find the other one first. So to break it down, bidirectional search is just an algorithm that runs two searches at the same time. You've got one search starting from the source, moving forward, and you've got another search starting from the goal, moving backward. And here is the absolutely genius part. When does it stop? You don't wait for the forward search to find the end. Nope. The second those two little search bubbles touch, the moment they intersect on even a single point, you're done. Game over. That single intersection point is all the proof you need. It's like that handshake in the middle of the maze. You know for a fact a path exists. And all you have to do is stitch together the path from the start to that meeting point and the path from the end to that same meeting point. Boom, you've got your full path. Okay, so now let's talk about why this is such a big deal, the payoff. We're not talking about it being a little bit faster. We are talking exponentially faster. This is where you really see just how ridiculously powerful this trick is. All right, let's look at the numbers for a sec, because this is where your mind is going to be blown. Let's say B is the number of connections each node has, and D is how many steps are in the shortest path. A normal, one-way search is going to take roughly B to the power of D steps. But with our meet in the middle trick, each search only has to go half the distance, right? So D divided by 2. And here's the crucial part to understand. When you're dealing with exponents, cutting that exponent in half doesn't just make things twice as fast. It's way more dramatic. So let's imagine a path that's 10 steps long, and every point connects to 10 others. A one-way search would have to check something like 10 to the power of 10 nodes. That's 10 billion nodes. It's insane. But with our two-way search, each one only goes 5 steps. So that's 10 to the power of 5 plus another 10 to the power of 5. That's what, 200,000 nodes? The difference between 10 billion and 200,000? It's just mind-boggling. So what this all boils down to is that the time and the memory you need drops from b to the power of d all the way down to b to the power of d divided by 2. And for any graph that's even moderately big, that is literally the difference between getting an answer in a few seconds and, well, never getting an answer at all. So, why should you care about any of this? Because this is so much more than just a clever algorithm. It's a whole mental model. It's a way of looking at a huge problem and knowing when to attack it from both sides. Now, it's not a silver bullet for everything, of course. It has a few conditions. You need to have a really clear starting point and the clear ending point. And the paths have to work both ways. You can't have a bunch of one-way streets. But if you meet those conditions and you use something solid like BFS for both searches, it's not just insanely fast, it's also guaranteed to give you the absolute best shortest path, every time. And that really is what I want you to take away from this. Forget the code for a second. This is a mental model for solving hard problems. If you're faced with this huge, impossible gap you need to cross, don't just start building a bridge from your side. Think about how you can start building from the other side too, and have them meet in the middle. So it kind of leaves you with this question, right? Think about it. Whether it's trying to negotiate a tricky deal or plan some massive project, or even just tackling a personal goal, what other giant problems are out there that we could solve way, way faster if we just stopped and thought, hey, what if we start from both ends at once?